Welcome to the first episode of Writing Wednesday, where I'm going through a piece of academic writing that can be a journal paper, a book, even a random article, not a random article, but like an article of interest. And to break it down a little bit, talk about the research methods, what's the findings, and etc. So for the very first episode, I am taking a look at one of my really good friends in biomechanics, friend in arms, Lance Brooks, his new paper, Unified Mechanical Framework for Evaluating Stretch Shortening Cycle Function. So a lot of words here. This is only a 10-page paper, so it might be more digestible for someone. But just to give a brief background in terms of like reading this paper, obviously go to his link on his Instagram profile and then get it for free for now at least. So the whole gist, I'm not going to read through all of this, but the idea is that the reactive strength index, it's a fairly limited variable to capture the behaviors of stretch shortening cycle performance that people want to capture. And sometimes it represents or really overinflates the benefits of one particular type of behavior that is very short ground contact times with tiny jump heights because of the way the math worked out. So in this sort of paper, there's a lot of sections that's kind of like the reason this metric behaves in this way is because the way the math works out, right? You can never go around the mathematics when it comes to discussing numbers that you generate, you measure, you calculate to try to achieve or track a specific outcome or behavior. So in this case, he suggested a different index based on Newton's laws of motion and projectile motion, things you might be familiar from your high school physics class that not all of you remembered, and essentially uses that to create a new different dimensionless quantity. So that's actually another part of this research that's very interesting because I did in my high school physics class dimensional analysis. That is basically different quantities of different variables. They have different units, right? Distance have meters, velocity has meter per second because of the way it's defined, right? The relationship between displacement and velocity is that velocity is a change in displacement over time. So different variables that you have are going to have different units. And essentially, if you mix and match different variables, either multiplying, squaring, dividing, square rooting in those like mathematical relationships and arrangements, you can arrange your number such that it's dimensionless. So generally, dimensionless quantities gives you a better representation of ratios between one thing with another because you're generally talking about the same thing. When things have the same units, the units cancel out each other and you have a ratio that's left behind. If you have literally apple divided by oranges, it's not going to cancel out well. But if you have two apples versus one apple, you're going to get a 2-to-1 ratio. So that's the idea behind having dimensionless variables. So I'm not going to go through this, so I'll just go through the introduction. And particularly one of the things I wanted to highlight is some of the problems that Lance stated that occurs with reactive strength index. So firstly, RSI, reactive strength index, it conflates variables of incompatible dimensions that actually surprised me because I always thought it's always flight time divided by ground contact time. But apparently, I guess maybe some people use this jump height divided by ground contact time. But like, if you do it right, theoretically, this shouldn't really happen. And to me, also, this is not like the biggest. I don't see this as the biggest weakness of RSI per se. Secondly, the form of RSI is not standardized when some uses flight time instead of jump height, which I think is more proper, and some using the ratio of counter movement and drop jump. So to me, that's like people just doing bad research or like having bad practice, right? Again, I don't think this is a as big a problem compared to number three, which I do agree with from a theoretical perspective, that when you have the contact time or the variable at the bottom of the divide sign, the denominator, if it gets short, it's gonna disproportionately inflate the values of the jump height or the values of the RSI compared to longer ground contact time and slightly higher jump height, but not as much. So that's almost the problem of like, what are you, when you generate a number, and I discussed this with the athletic index as well. It depends on what you want to get out of your metric of interest. What behaviors are you trying to capture, A, and what behaviors are you trying to encourage, B. Because generally, when you work with an athlete or coach, Bigger numbers, the better, right? Bigger is the better. We all know that. But the manner through which the numbers gets inflated or deflated are really, buffed or nerfed from a gaming perspective. That's very important to the behaviors of the athlete that's going to happen. And another thing that's not really touched on in the introduction, but it was mentioned a lot more in the method section, is if people wanted to use an RSI from a drop jump, you almost kind of have to include the height of the drop into the equation itself. Obviously, as is, it doesn't include it. But think about it, if you have a higher jump height from the box that you drop down to, you're going to have a greater demand in order to handle that velocity, reverse it, and even jump the same height, even within the same constraint of time, right? Because you needed to do more. Here, it's like you needed to overcome or dissipate more kinetic energy, overcome more downward momentum. So, let's go into the method. The true spirit of it is very simple. It all starts with Newton's second law in the vertical direction. So you have the net force equals to the gravitational force you generate pushing down minus your weight, and that should equals to mass times acceleration of your body. No news here. Then we are trying to get the velocity at takeoff, which then tells us the height we are jumping at. So that's sort of this point where velocity at takeoff, assuming roughly constant acceleration. I don't know how much that matters, to be honest, because it's 8 p.m. and but this is one assumption to keep in mind for the mechanics cycles. Assume constant acceleration or even average acceleration, right? You can calculate average acceleration for your forces, multiplied by the time of ground contact, time available for force application, which is the same as time of ground contact, I believe. Yeah. Even though obviously one thing I need to clarify is like not all time you spend on the ground is generating meaningful upward force to overcome gravity. You can generate force against the ground that's less than what gravity is doing, and you're not going to leave the ground that way. You have to beat gravity, like I said many times before. You have to beat gravity in order to jump high. And then here, the highest center mass achieved during the flight phase, that depends on takeoff velocity. So that's talking about the displacement from the height of takeoff, right? Because obviously the absolute height, as I mentioned before, absolute height depends on two things: the height of the body center mass at takeoff and your takeoff velocity. But here it's just a raw displacement. As here, equation 3 defines vertical displacement as a function of both the magnitude and duration of net acceleration. That's just simply substituting in the variable here. And then they just do a little bit of a rearranging to make sure the variables you have ended up being dimensionless. And here it's talking about the effective upward displacement, h, relative to the displacement expected on the gravity over the same squared stance duration. So here you have the height you jumped and how much time you have. That's it. That's as simple as it is. And what's really nice about this is these variables are fairly readily available. Like whatever devices that already computes these things using time, you can already do it. And the RSI is simply substituted with the same variable, so we can calculate it differently. So again, it's about how the math ended up working out. Where's the really nice picture? So here's how the math ended up working out. Okay, you have the new variable. I know here it has the height of the drop as a bit of a spoiler, but basically it's considering how much you jumped and how much you overcame. So that's the total amount of, if you think about it from the energy perspective, remember gravitational potential energy, right? You're overcoming the gravitational potential energy that you lost in the jump that you have to handle, plus the new gravitational potential energy you have to generate. That's like almost like the total energy. And then here's how much time you have to do it. Essentially, not perfect explanation, but that's the general gist. I hope that's helpful. So here, yeah, extension to drop jump conditions. Obviously, if you don't drop, right, this goes to 0, and then you have the base term. But if you ever drop, it just adds to the top, and in a way, the higher you drop from, keeping everything else constant, the ratio is going to reward you. So this is important, okay? The metric of interest is rewarding you for behaviors that's for a challenging context that you successfully handled, you're going to get a bigger number. So it's a good thing. It's trending in good direction. And here's the I guess I still find it a little bit weird that people don't just always use flight time, but I don't think it changes too much because we know the relationship between actually height and flight time. Is it mentioned here? No, no, because you need the takeoff velocity. I guess this one. So, right, you have the relationship between velocity at takeoff and height. So you can, but it's not flight time. Okay, so never mind. The flight time was never in this equation. I wonder, just curiosity wise, if you swap h for flight time, are you going to get similar things? I would assume so, but APM brain, hard to figure out. Okay, so what's really fun? Okay, how do you demonstrate this new measurement is going to be successful? So here, Lance basically did a simulation, or really, it's called like a grid. It's not like a grid search. So it's like a grid simulation or modeling, where it's taking a range of biologically plausible metrics of ground contact time, jump height. 1 meter jump height from a drop jump is cracked, by the way. That's why it's a model, it's simulation. And then drop height of 2, 3, 4, 5 decimeters. I bet you haven't heard that word in a while. And here it just sort of maps the values of the different indices to the ranges of contact times and jump height. So let's take an example. Automata time of 0.15 meter, sorry, 0.15 seconds. Obviously, the longer it is, the higher you're gonna jump. Makes sense. But what's kind of annoying is like for the same jump height, right? The value of your RSI, sorry, the value of RSI is going to get higher and higher, even though you aren't really jumping higher and you are just using the short contact time. Which again, I mean, if you it is a problem at like super small values. I don't know if it's as clearly demonstrated in this context for me personally. Because the behaviors we see with the DRI, it's just like, yeah, we are almost disproportionately penalizing shorter ground contact times if you don't have a jump height. Mm. So it's just again the way math shakes out, right? This ends up having a better behavior at the more extreme ranges compared to RSI. So this is turning it into, oh, this is a funny one, by the way. I have a feeling that this figure comes from a reviewer. Be like, oh, you have this figure where you modify the jump height and you look at the behavior of the DRI index because jump height is part of the equation. Why don't you do the same thing for RSI, which mathematically obviously does not care about drop height? That's why you have four identical figures. This very much smells like a reviewer acting up, okay? Unless Lance, you are just that rigorous. I don't know. But this to me just be like a reviewer writing a question without fully understanding the math, where I've experienced that too. All right. So if that is the case, my condolences, boss. So this is kind of hilarious. Like clearly this doesn't depend on the drop height. Like what especially in a modeling scenario. It's not even like real data. This is funny to me. Okay. So regardless, what do I want to talk about next? Okay, here. So here's how this can be used, okay? Based on different variables that you do have. So your inputs, that's like the raw signals. A lot of times is literally just going to be time. So here you're going to have your contact time, aerial time. These are likely going to be provided, or these are sort of captured directly. Like these are as close to raw data as you're going to get. Drop height, you know. You can convert the aerial time to jump height with a very simple calculation. That's literally how just jump map works. That's going to be how OVR machines work. Anything that depends on time, that's how it works. And you just apply these equations. Aerial time TA. Okay, so there's a relationship between aerial time and that's here. So bang, you always have the same. This is also kind of funny, right? You could just have like a joining, like a converging box, but it's okay. The cosmetic fun stuff. Vertical force. Now these are only available if you have force plates. So you need to again use your impulse momentum relationship. What do we say about impulse? Impulse is integral of impulse is integral of force with time. So bang, you have your J impulse. And then you have your time. Okay, take off, toe down, sure. That's your events. Did they say, oh, he didn't even like put the explanation for these shorthands. Anyway, I love the nitpick if you haven't seen. You calculate your vertical takeoff velocity from your impulses and your height. You have your height and then bang. Okay, cool. So overall, very fun paper. I love seeing the mathematical nature of deriving the metrics. Obviously, when you change the equation, you should expect different behaviors based on the same sets of input data, right? I think it might still run into issues with a very short ground contact time, but having a G in front of it being a 9.81, that does like within a biologically feasible very values of time, multiplying by gravity can help, right? It does make it literally 10 times bigger. So you're gonna have less of a problem, even if it's squared, you're gonna have less of a problem with smaller, shorter ground contact times again within biologically relevant scenarios. Obviously, if you want to take it to the extreme theoretical, chuck in very, very small times, you're gonna have the DRI blowing up the same way RSI would because you cannot divide 1 by 0, right? But nobody jumps off the ground in 0 seconds, not even if you're trained by THB. So anyway, that was the review for the first Writing Wednesday. Thank you very much, Lance, for your great work and published in the European Journal of Sports Science. Congratulations. I think it's one of your first papers in as a new faculty. So as a new faculty myself, love to see it. All right, I hope you guys enjoyed this video and I'm gonna stop the recording and see you next time.